Hello, in this video I wanted to look at Chapter 17, Section 5, all about resonance and standing waves in tubes. So first I want to look at interference with waves. Now we're going to be talking about sound waves specifically, but this is true for any kind of wave, whether it's in water or sound or much more complicated ones. So if we've got two waves, they can interfere, and there's kind of the two far ends. If we've got perfectly constructive interference, we've got the high points here that exactly line up. They're going to add up, and we're going to end up with a wave that is twice as tall. On the far end of the spectrum, if our high points line up with our low points, they're going to interfere what's called destructively, and we're going to end up with basically nothing. They're going to cancel out. And of course, there's all sorts of room for waves in between here, where they interfere a little bit constructively or a little bit destructively. This is just kind of perfect interference as far as constructive interference, and perfect destructive interference where they line up perfectly. And so we've got whole range, everything in between there. For what we're talking about, we want to look at, we've got a tube, and we'll start with one that's closed at one end. And if we've got a sound, vibration, coming in one end, the wave is going to come in, it's going to bounce off the far end of the tube, and then it's going to go back out. But there's still more wave coming in, and so we've got wave coming in, reflections coming out, more wave coming in, more reflections going out. And if everything is just right, those reflections coming out are going to get met by the new wave coming in, and they're going to interfere constructively so that everything lines up really good, and we'll end up with what's called a standing wave, where everything lines up just perfectly, and we end up with a wave that is filling the tube. So this is going to be, I'm not even going to try to draw it. I've got pictures on the next page. We end up with a nice wave. It's called a standing wave, where we have, I'll just show the picture. So like this, we've got what's called a node at one end, where the wave just, it doesn't move. Okay, our total wave is always going through that point, so that's a node. Then at the other end here, we've got an antinode. And that's where we've got the maximum displacement away from the center. And so for the tube, it perfectly fills the tube, and we end up with a node at one end and an antinode at the other end. Now it turns out that based on the length of the tube, we can figure out exactly what wavelength we need to get this static wave, where everything lines up nicely and the waves coming in and the waves going out interact in such a way that we get a standing wave. And for a tube that's closed at one end like this, we need our wavelength to be 4 times the length of the tube. Okay, so our wave, all the way out here, one wavelength is 4 times as long as the tube is, and that's when we get this resonant frequency, where we get a standing wave inside the tube. Okay, now there's more ways that we can get a node at one end and an antinode at the other end. We can fit a whole nother chunk in there. Okay, now notice that to have this node at one end and still have an antinode at the other end, I can't just cut that wavelength in half. I actually have to divide it by 3, and then I get 2 nodes, one here and one here, and 2 antinodes. Okay, but there's no way to just cut the wavelength in half, because we can't get the node and the antinode, one on each end. And then we could keep going. We can't do an even one, because we need a node at one end, antinode at the other. But I can divide that wavelength, the original one, by 5, then I can fit a whole nother set in there, or by 7 and get a whole nother set, or any odd number. Okay, so this first frequency, where the wavelength is 4 times the length of the tube, that's the fundamental frequency. And then after that we get our overtones. Taken all together, they're all the harmonics. So first harmonic is the fundamental frequency, and then the first overtone is whatever harmonic, like this would be the 3rd harmonic, because we had to divide our wavelength by 3 to get it. That'd be the 5th harmonic and the 7th harmonic. Okay, so for a tube closed at one end, we cannot get even harmonics, they're all odd. And to deal with this situation where we've got different harmonics, we've got this formula where n is what harmonic we're at, L is the length of the tube, and this VW is the speed of the wave. But since we're going to be talking about sound here, it's the speed of sound. Now, it's important to note that the speed of sound does change with temperature, so depending on what temperature it is, the tube will resonate at a different frequency. Okay, so if all we're dealing with is the fundamental frequency, we can ignore the n out in front, and we just take the speed of sound divided by 4 times the length of the tube, and we get the fundamental frequency, and then if we just multiply by odd numbers, we can get all of the harmonics, all of the overtones. Okay. Now that changes slightly for a tube that is open on both ends, because now when it's open on both ends, the wave coming in is just bouncing off of air at the other end, and we end up with a node in the middle and then an antinode at each end. Okay. Now for that to happen, we look at it, and I don't have the wavelength all drawn out this time, but it's only going to be, or the wavelength is only going to be 2 times the length of the tube rather than 4 times as it was before. And so now, because we need an antinode at both ends, we can actually fit any multiple in there. So I can have a second overtone. Okay, so I can fit a whole nother set in there. I can have 2 nodes and 3 antinodes. Or I can do, or sorry, I said second overtone. We can have the first overtone, the second harmonic, and we can have the third harmonic where we get 3 nodes to fit in there, and we still have an antinode at each end, and then 2 in the middle, and so on and so forth. So for a tube that's open at both ends, I can have harmonics that are either even or odd. So I can actually have the first, second, the third. Unlike with the closed tube, I could only have the first, the third, and the fifth. Okay. So I just wanted to kind of show what I was talking about in this little simulation here. Up top, I've got the wave coming in, and then later I'll be able to show some reflections as that wave comes in. Let me close this. Comes in and bounces off the end of the tube, and then reflects back, and then reflects from the air outside the tube and reflects back. I'll be able to show all those reflections. And down below is just the sum of all of those waves as they interfere. So right now I've got a tube length of 2, and my wavelength is 5. So we kind of know that this is not going to give us a standing wave. If I turn on a couple of these reflections, we can see that as the wave comes in and reflects back and then reflects back, they are really not lining up. Okay, we've got waves kind of all over the place, and our resulting wave as we add them all up is not a very big one. They're definitely interfering destructively here. If we remember back to the formula, I should be able to get a standing wave in this tube if my wavelength is 4 times the length of the tube. So if I change this 5 to an 8 and run it again, now I've got all of these waves. They're still all showing, but we just can't see them because they're in sync now. My incoming waves and my reflections are overlapping each other, which is resulting in this standing wave down here where I've got the node at one end and the antinode at the other end. Okay, so if I change that even a little bit, if I go 7.9 and run it again, I'm no longer exactly on the fundamental frequency, so you can see these waves are off by just a little bit, and my standing wave doesn't quite go all the way. Emphasize that a little bit farther out. So it's not perfect as I change that and go down. I should be able to get the next harmonic, which remember in a closed tube I can't do even, so I'll have to go up to the third one. If I take 8 divided by 3, and my new wavelength should be 2.66. And now everything's interfering nicely, and I've got a standing wave with 2 nodes and 2 antinodes. Okay, and I could keep going. I could then divide 8 by 5 and get the next harmonic. But if we go ahead and pause that, we'll move on to a tube that's open on both ends. Okay, so if I run it right now, we're definitely not going to get a standing wave, okay, because the relationship is different for an open tube. If I want it to be the fundamental frequency, I need my wavelength to be double the length of the tube. So if I change that to 4 and now I run it, I do get a standing wave, and I've got a node in the middle and an antinode at each end. And just like before, now I can work my way up through the harmonics, only this time I can do evens as well. So instead of 4, I could do 4 divided by 2 for second harmonic, and now I've got 2 nodes, 3 antinodes. I could do 4 divided by 3, I could have 1.33 in here for the third harmonic. Okay, and now I've got 3 nodes and 4 antinodes. Okay, so hopefully that kind of illustrated what I was talking about with the waves interfering and being able to predict what the harmonics are just based on the length of the tube. And for all of this, I was just assuming that the speed of sound was 343 meters per second, so that might change depending on the problem. You just have to remember to work that in. And that's in this formula here for the speed of sound. Okay, so I want to go through an example real quick of using this formula. So if we read through this, we know what the fundamental frequency is, we're trying to find the fundamental frequency. We know what the length of the tube is. We know that it's open at both ends, so I brought this formula in from before. And we're given the speed of sound. So remember that changes with temperature, but they've just given it to us, the speed of sound. So fundamental frequency, that means that n is going to be equal to 1. We're looking for the first harmonic here. So I can have a 1 there. I don't really need it anymore. And speed of sound, 344. And 2 times the length of the tube, so 0.672. And when I divide that, I can find my fundamental frequency. So plug this in, divide it, and I get 256 hertz. Okay, so the formula is fairly straightforward to use. I just need to know the speed of sound and the length of the tube, and I can find the frequency. Or I can go the other way. If I know the frequency, then I can plug in whatever other information I know, and I can work backwards to find that. To answer the second part here, if I want the frequency of the second harmonic, it is just going to be double this one. So for part B, second harmonic, I just double that, 512 hertz. Okay, so pretty simple to find the other harmonics once you know the fundamental, or you can work backwards. If you know, say, the third harmonic, you would just divide by 3 to get back to the fundamental. Okay, so that's kind of the quick overview of looking at resonance in tubes, the difference between being open and closed, and what a standing wave is. Remember nodes and antinodes, all of that. Thanks.